Welcome back to the 6th episode of the Artificial Vision Systems course. In the last episode, we finished the camera element by talking about color images. In this episode, we'll move on to a new element and talk about optics, the element that can improve the light information entering the camera. Let's start by defining what an optic is. An optic is a set of lenses capable of deflecting light rays so that they strike the camera sensor in an orderly fashion. Ordering light rays means obtaining focused images, which is precisely the main objective of optics. Let's now define the main parameter of optics, the focal length. The focal length indicates the optic's ability to deflect light rays and is linked to the curvature of the lenses that compose it. Optics with different focal lengths mean optics that are able to deflect the light rays entering the optic itself in different ways. By definition, focal length is the distance between the main axis of the lens and the focal plane, if the light source is very far from the lens. The main axis of the lens is the area in which the light rays are actually deflected. The focal plane, on the other hand, coincides with the plane where the camera sensor is positioned. At this point, let's pause with vision systems and understand how lenses work. We will do this by adopting some simplifications. To talk about lenses, we must first define some quantities. A lens is an object made of a certain material with a refractive index NL and a certain diameter. The lens is formed by two surfaces, S1 and S2, which have a certain curvature R1 and R2. The two curvatures are not necessarily equal. The lens also has a main axis, which divides the two surfaces that compose it. It is usually placed inside an optical system that itself has an axis. Finally, the optical system is divided into two distinct areas along the axis, an object plane, in green and by convention to the left of the lens, and an image plane, in red and by convention to the right. The entire system is placed in an environment that also has its own refractive index. Usually, the environment is composed of air, with a refractive index equal to 1. To understand how lenses work, we refer to geometric optics. To do it simply, however, we must resort to two simplifications. The first is to consider paraxial optics, so we will consider all light rays as straight, and when their direction changes, we will continue to consider them straight. The second simplification is related to thin lenses, so we will consider all our lenses as having a very small diameter, tending towards 0. Under these two simplifications, let's now see how lenses work. Let's assume we have a point in the object plane, to the left of the lens, that emits light, meaning light rays. Furthermore, let's assume that this point is placed at a very great distance from the lens, at an infinite distance. The light rays emitted from this point will reach the lens parallel, be deflected by the lens, and converge, meaning they'll intersect, at a point distant from the lens, exactly one focal length away. Now let's take the point we placed at infinity in the object plane and move it closer until it reaches a distance that is no longer infinite. The light point, which we'll now call P1, is now at a distance equal to SO1 and at a height from the optical axis equal to Y1. The light rays starting from P1 reach the lens and are deflected by it, crossing at a point P1' at a distance SI1 from the lens, greater than the focal length f. The height of P1' relative to the optical axis will finally be Y1'. Let's move point P1 again and see what happens now. The point, now called P2, is at a distance from the lens equal to SO2 and at a height from the optical axis still equal to Y1. The light rays starting from P2 reach the lens and are deflected by it, crossing at a point in the image plane called P2'. P2' is at a distance from the lens equal to SI2, which is greater than SI1. The height of P2' relative to the optical axis will instead be equal to Y2', which will be even greater than Y1'. Now let's try to move the point in the object plane even closer until it reaches a distance from the lens exactly equal to the focal length and see what happens. In this case, point P3, placed exactly at a distance equal to the focal length from the lens in the object plane, will emit rays that will be parallel to each other, and therefore will never cross in the image plane, or rather. They will cross at a point located at infinity in the image plane. We have now reached a distance equal to the focal length. Let's try to get even closer and see what happens. In this case, the rays starting from P4 will diverge in the image plane and therefore will converge at a virtual point still located to the left of the lens and thus in the object plane. Let's recap all these behaviors. A light ray coming from a distant point, from infinity then, converges at a distance equal to the focal length. As the point in the object plane moves closer, in the image plane it moves further away and the height increases. A point distant exactly the focal length from the lens focuses at a very large distance in the image plane, equal again to infinity. Finally, a point located at a distance less than the lens's focal length focuses at a negative distance in the object plane, because the rays in the image plane diverge in this case. So, is there a model, a mathematical relationship, that describes all of these behaviors? Of course, the mathematical model exists and is shown right here. The inverse of the focal length is equal to the sum of the inverses of the object distance in the object plane, SO, and the image distance in the image plane, S phi. This formula is very important because it relates these three parameters, focal length F, object distance SO, and image distance SI. Naturally, by using the inverse formulas, we can find one of these three parameters if we know the other two. This relationship leads to a graph that looks like this. When I'm on the right side of this graph, meaning the object is very far from the lens, the image will form at a distance exactly equal to the focal length, which is 50 millimeters here. The closer the object gets to the lens, the more I move from right to left on this graph, and the further the image moves from the lens, reaching an infinite distance when the object is exactly at the focal distance. At this point, if the object gets even closer to the lens, the image will no longer form in the image plane, but at a negative distance from the lens, and therefore in the object plane. Thanks to this analysis, we now have a relationship that links the object parameters, the lens parameters, and the image parameters. Now we must try to use this relationship in a real system, where the object is a real object, the lens is the optics, and the image must be in focus exactly on the camera sensor. But we will see all of this in the next lesson.